Welcome to Study Time, a televised home learning program produced by Rwanda Education Board.
Hello, dear students. Welcome back to this TV learning series program. I'm Teacher Patrick once again, and I will be with the Senior 3 class, and we'll be revising together. You remember in the previous lesson, that's what we were doing. So I want us to continue revising and do the unit assessment until we feel probably it's enough for us. So we are doing still, also this must be unit 5. That is not unit, I have to make a small change there. That is unit 5. That is unit 5, but it is lesson 6. So we'll continue with the assessment. We're doing the exercises, and by the end of the at least 30 minutes that we are together, I expect you to contribute to the questions that we'll be answering together. I expect you again to have your exercise books with you ready, have your notebooks, and probably if you have a calculator with you, be ready with that calculator. So today I will not go through what we did in the previous lesson, because you remember we are answering the questions, and we are still continuing to answer the questions together. So let's straight away go to the question number 1 that we are going to do together. It's saying, in a class experiment to study the rate of a reaction, 2 grams of manganese 4 oxide was added to 50 cubic centimeters of diluted 20 volumes of hydrogen peroxide solution at 25 degrees Celsius. The volume of gas produced was measured at 10 seconds intervals, and the results obtained as follows. So the results are here. We have the time, 0, 10, 20, 30, up to 80, the intervals of 10. And the volume of the gas produced. Of course, at 0, before you start the experiment, the volume of the gas is 0 as well. So at 10, 60, 20 seconds, this was 90. Those are the volumes of the gas. Which gas? The gas is produced in the reaction. That is the first question. Name the gas produced. So we'll have solutions. Solutions to the questions. Number 1, part A. I will be giving some few seconds to think about the gas, to think about the question as we go along. Name the gas produced in the experiment above. So what was the experiment, if you remember? The experiment is about the reaction. It is the decomposition of hydrogen peroxide by using manganese 4 oxide as a catalyst. So the gas that is produced is oxygen gas. So that is the gas that is produced. B, write equation for the reaction that took place. Write equation for the reaction that took place. You remember from the previous slide, we said it is the decomposition of hydrogen peroxide. So decomposition of hydrogen peroxide, it is decomposed in the presence of manganese 4 oxide. So you have to keep remembering the question. That's why I was even reading it. So it is hydrogen peroxide, 20 volumes of hydrogen peroxide were decomposing. They decompose into water plus the oxygen gas. That is 2, oxygen, 2, plus the oxygen gas. Manganese 4 oxide. Manganese 4 oxide. So that is the oxygen, the reaction that is showing the decomposition. Plot a graph of volume of gas produced against the time and label it this A. I'll just skip a bit and then go to the this is the graph that is produced. This is the sketch graph, the graph that I was just trying to draw. If you look at the graph, this is how it goes. And these are some points that were plotted. And then that is, we said it has to be labeled A. So we are using the values. These are the values. The values we used to plot the graph are the values in the table. The time and the volume of the gas. So it is the volume of the gas, that is the x-axis, the y-axis, and then you have the time taken, which is, this is the time taken here. The time taken is in seconds. Whenever you are plotting the graph, there are some important points that you need to remember. Label the scales. So this is the y-axis, and it is the volume of gas, or the volume of gas is measured in cubic centimeters. So whenever you label it, so the labeling must include even the units of any variable that you are dealing with. So the time can either be in seconds or minutes, and then the volume of the gas. We have seen the graph goes like this. And we are supposed to label it A. So this is what we are asked from the graph. This is just a sketch graph of what is produced. This is the graph that was indicated. And then we probably go to the next question, because we'll come back to that graph again, because we have to use it several times. Use the graph to find the volume of gas produced before 35 seconds. So moving down to the graph, before 35, there is time here. So we have 10, we have 20, this is 20, this is 30. So they said before 30 seconds. So before 35 seconds. So 35 is here. So what you do, if this is 35, this is 35 as an example. So draw a perpendicular line or a straight line until it touches the curve. And then again, using a ruler. But of course, if you are using the graph paper, it is better to use a graph paper. To get the accurate values, you will need a graph paper. Otherwise, if you use a plain paper, you won't get the exact, accurate values. So here, before 35, the question was asking us to use the graph to find the volume of the gas produced before 30 seconds. So we are moving. This is the volume of the gas here. So you read the volume on this point. That will be the volume that is produced before 30 seconds. Time to produce 100 cubic centimeters of the gas. Time to produce. So you have to go to the volume, to the y-axis, where there is, that is the volume of the gas produced. Now you look for that 100 cubic centimeters. For example, if you are moving down, so you just come here. This is 100. Then you draw, assuming 100 was here. If this is 100, that is an example I'm just using. That is not 100, but I'm just using it as an example. Assuming this is 100. So you draw a line, a straight line, touching the curve. And then again, draw another line, moving down to the time axis. So this is the time. Now you read the time that is used. You read this time here. This is the time that is required to produce 100 cubic centimeters of the gas, because the cubic centimeters of the gas is over there. So that is what you were expected to do. Explain why the volume of gas does not exceed 120. So this is around, if you move along this line here, this is the maximum. And this one, I'm assuming this is 120 cubic centimeters. And then we're saying, why doesn't it exceed 120? Why is it so? At this point here, when the line or when the curve now becomes constant or becomes horizontal, it means that the reaction is over. It means the reaction is over. Explain why the volume of gas does not exceed. So it means that the reaction has ended. That is the end of the reaction at this point here. So that is part E of the question. So the reaction has ended. Oh, that is the end point of the reaction. Reaction ending means what? Hydrogen peroxide is no longer decomposing. So the amount of hydrogen peroxide in the reaction flask has all been decomposed into water and oxygen gas. So that ends the reaction. And therefore, there will be no change in the volume of the gas that will be produced. Sketch a graph of B on the same axis to show the results in the experiment. If the experiment is repeated at 35 degrees Celsius instead of 25 degrees Celsius. So we're assuming this was 25 degrees Celsius. That is the first graph that we drew. Now, the first graph we drew, the experiment was taking place at 25 degrees Celsius. Assuming the temperatures now have been raised, what happens? So that means the rate of the reaction would have to increase, and we would expect the graph to move. So it is the same. The reaction starts at the same time, but this one is occurring much faster. So this one moves in that case. So when you have such a case, you see these reactions, this one has got, this one is much faster than this one, and these reactions are all ending at the same time. But one is faster than the other. So we said we label this one B. So this one is labeled B. So it should be slightly above this A because of the high temperature and high increase in the rate of the reaction. So that is why it is slightly above this A. If at all, the reaction probably was moving like this. Maybe if it was moving, that's an example. It's not part of the question, by the way, but I'm just giving it as an example. If this reaction was moving like this, it means this reaction here and this reaction here, they are quite different. Different reactions. But if these reactions are starting from the same time and when they are ending, one ends faster than the other because of the speed of the reaction, but they connect at the end of the reaction because the volume of the gas that will be produced at the end of the reaction remains the same. It is only the speed that increases. So this means that these two reactions are the same, but occurring at different conditions. These may be different. These are different reactions, even at different conditions. That is the main important point that you should remember. The next question, the mass of manganese for oxide after the experiment remained constant. I think after the experiment remained constant. I just want to make that one a bit more clear. Remained constant after the experiment. Did I miss something? Remained constant at the end of the experiment. So why is the mass of manganese for oxide remaining constant? This is the mass of manganese for oxide that we started with. 2 grams of manganese for oxide. And at the end of the reaction, the mass remained constant. Why? Manganese 4 oxide is a catalyst. And what is a catalyst? Catalysts only speed up the rate of the reactions. They don't take part in a chemical reaction, and they remain unchanged at the end of the reaction. So that is why the mass of manganese 4 oxide remains constant. So the mass of manganese, so I've already answered F, and G was asking why is the mass of manganese 4 oxide at the end of the after the end of the reaction remaining constant. So manganese 4 oxide is a catalyst and remain unchanged at the end of the reaction. At the end of the reaction. You remember what we talked about, the effect of the catalyst, and we said catalysts only provide the alternative route, and that alternative route must be a shorter, that is, provides a shortcut for the reaction to take place. That's why catalysts increase the speed of the reaction. So we'll just go to the next question, which is question number 2, almost similar to that one, so I wouldn't expect a lot, maybe a lot of different questions. Copper 2 oxide catalyzes the decomposition of hydrogen peroxide. So manganese 4 oxide is not the only catalyst that can be used. So that is why I brought this one. So you should know that it is not only manganese 4 oxide that can be used to catalyze this reaction, hydrogen peroxide. There are some other catalysts. And we are saying copper 2 oxide is one of them. Probably we can also mention, along with the answering of the questions, maybe we'll be able to mention some other catalysts that are used. Decomposition of hydrogen peroxide. 0.5 grams of oxide was added to a flask containing 100 cubic centimeters of hydrogen peroxide solution. A gas was released. Which gas? Oxygen gas. It was corrected and its volume noted every 10 seconds intervals, and this is the table of the results that were produced. Look at the table of the results. 0, 0, 10, 18, 20, 30, 30, 40, 40, 48, 50, 53, 60, 70, 58, 80, 58, 90, 58. What does it show? So the values should give you the idea of how the graph looks like. As time increases, you see the volume of the gas is also increasing. But reaching somewhere around 70, time increases, the volume of the gas remains constant. What does that mean? So it should give you the idea. So the first question is asking, what is the catalyst? We have mentioned about the catalyst. Or maybe because we are answering questions, we can also even put it there. This is number 2, which is asking, what is a catalyst? I believe, at least because we have mentioned the catalyst several times, and I'm expecting at least everybody to be able to define what a catalyst is. A catalyst is a substance that increases the speed of reaction and does not take part in a chemical process and remain unchanged remain unchanged at the end of the reaction. At the end of the reaction. That is simply the cut. We had talked about this one several times. Draw a diagram of a suitable apparatus for this experiment. A suitable experiment. So you have manganese, so you should expect you have a flask. This is a flask, and in the flask there, you will have manganese 4 oxide. You have copper 2 oxide, not manganese 4 oxide, and then hydrogen peroxide being added. You are adding hydrogen peroxide in this flask, hydrogen peroxide being added. What else do you need? You also need to add manganese 4. So in here you have copper 2 oxide. I usually always, because manganese 4 oxide is the most common one, so I tend to forget. So this is copper 2 oxide. Copper 2 oxide, we said this is a catalyst, and you are adding hydrogen peroxide. So what happens? You correct the gas. How do you correct the gas? You may have a calibrated cylinder. Maybe this is a calibrated. You have to connect this one to a calibrated cylinder, measuring cylinder. This is a measuring cylinder over here. Oh, that's the diagram. So this is a measuring cylinder which is calibrated. And this one can be even corrected over water. So you have this. Or you have. This is calibrated cylinder with some values, and you are correcting this over water. Oxygen doesn't dissolve in water, so you expect the gas to be correcting here. So you'll be recording after certain time of intervals, 5 seconds, you record the time. Make sure you have to close these areas so that you don't lose the gas during the experiment. So all the gas that is produced here is corrected. Name the gas produced. We had named the gas already before. So that is part C. So we said the gas is oxygen. And write the balanced equation. We had even written the balanced equation for that reaction before. So balanced. This time we'll have copper 2 oxide. That is the only difference that we have. Oxygen. This is water, and the oxygen gas that we are correcting there. And then you have plot a graph of the volume of the gas. I said you already have the sketch graph. You have already the sketch graph of that reaction. Where are we now? This is so this is the sketch graph is similar to this one. So if you ask, you're plotting a sketch graph against time, so it is a similar sketch graph, sketching the graph. So you have, it will move in the same way as it moves, so you have the same, it is similar. So you have the volume in volume of gas in cubic centimeters, and you have time here, and the time is in seconds. So it is still, describe how the rate during the reaction describe how the rate during the reaction can be increased. I think that is what was supposed to be. How the reaction can be increased? How can you increase the rate of the reaction here? So you either were using a catalyst, which else? So you can either increase, so that is part F. So you increase the concentration of hydrogen peroxide, or what else? You can even increase the temperature. That means you heat the reactants over here. Increase the temperature. Those are some of the factors that you can also. G, what happens to the concentration of hydrogen peroxide as the reaction proceeds? When the reaction is proceeding, the concentration of hydrogen peroxide is reducing. So you need, that is J, the concentration of hydrogen peroxide, reduces as the reaction proceeds. So that is why it reaches somewhere and then has to. So you determine the rate of the reaction at 30 seconds. You remember I said if you have 30 seconds here, then you move at 30 seconds. So I'll just consider this one. Then may just look at the volume, the sketch graph. So this is, so here you will have to draw, make sure, move from the 30. Now if this is 30, so you are moving from here, if assuming this is 30, you draw a straight line, touches here, and then draw a tangent line. So that tangent line, you find the gradient of that line. Change in y, so you have to look for the gradient. Either moving here, you have to look for the gradient. Change in y, over, you move from here, this will be the change in x. So the change in y over change in x will be equaling to the slope, which will be equaling to the rate. Make sure you have reaction, you have the proper graph, which will give you the correct values. What chemicals are present in the flask after 90 seconds? Here, if it is moving like this, the reaction, if you remember how it was, or this is how, remember this was like this. Oh, no. This is how it was. These are the values. After 90 seconds, what do you expect? What do you have in the flask? There is only water, and oxygen has been corrected. So you remain with water and the catalyst that you also used. So that is what will be remaining. What mass of the copper 2 oxide would be left? The same mass, 0.5 grams. Sketch your graph, the curve that might be obtained for one. So there is no change in the, increasing the amount of the catalyst does not change the speed of the reaction. So it remains the same. Name other substance that characterizes this decomposition. We had mentioned manganese 4 oxide. We can mention potassium permanganate. We can mention potassium iodide, and so on. For today, we'll have to stop here. I hope we'll be together next time. And probably we'll have some other questions as we assess ourselves in this unit. Thank you so much for watching and listening. Have a good day. Bye.